Hello, welcome back to our course, Electronic System Design. Okay, today we will be in the last topic, that is heat dissipation. Heat dissipation is also one of the important concepts in the, one second. So heat dissipation is also one of the important topic that we have covered today. Heat dissipation. Okay, see here, this is heat attainment, how heat should be transferred, how you can protect your devices from the excessive heat. That is also one of the important factors. Between the components to components, more energy is transferring from a lifetime. Maybe it causes some damage. That is clip to device, clip to PCB, snap and stampings, double-sided tapes, solder or adhesives. So thermal interface resistance minimized using grease or pad and by making surfaces as flat as possible. Okay, that we will see. So these are the heat sinks. Will help you protect our devices like computers, transistors. See, this is the transistor symbol. The heat sink is attached. And a LED. LED bulbs are also, you already know. So this is the bulb and this is the heat sink. And water heat sink. So this is the water heat sink around it to protect these devices. By continuously heat means what will happen? It may get damaged. Heat sinks are devices that enhance heat dissipation from a hot surface, usually the case of heat generating component, to a cooler ambient, usually air. So, how hot surfaces becoming close means the air is flowing into it. So, we will see for following discussions. Air is assumed to be the cooling fluid, right? In the most situations, heat transfer across the interface between the solid surface and the coolant air is the least efficient within the system. And the solid air interface represents the greatest barrier of heat dissipation. So here the main fluid and main interface is the air only. The solid air also one of the most important barrier for heat dissipation. The primary purpose of heatsink is to maintain the device temperature below the maximum allowable temperature specified by the device manufacturers. The primary purpose of heatsink is to maintain the device temperature below the maximum allowable temperature specified by the device manufacturers. So it is passive heatsink. You can see here the figures used in natural convection applications or in application where heat dissipation is not dependent on design supply airflows. So these are active heat sinks. Fans are designed for its own use. Reliability is dependent on moving parts. One big negative, if your fan dies, you need to replace the entire unit. No problem. Semi-active heat sinks leverage of existing fans in the system. Usually a passive heat sink set in front of the fan to produce vertical flow that we will see. So this is stampings and it is casting. Stampings are copper or aluminum sheets stamped into the desired shapes. It is a like a stamp, no shape is stamp. So it is useful in the low cost solutions to low density thermal problems. Casting high density aluminum or copper, sorry, bronze fins are produced with stand, lost core or die casting, may or may not be vacuum assisted, allows for a maximum performances with impingement cooling. More expensive but can make odd shapes. AI allows used to have lower conductivity than AI allows used for extrusions. So what is extrusions here? So this is what the shape. So extrusions allow for formation of elaborated 2D shapes capable of dissipating large heat loads. Cross-cutting to produce rectangular pins may increase performance by 10 to 20%, but the extrusions rate will be slower. So design limits usually set fin height to gap aspect ratio, min minimum fin thickness to height, maximum base to fin thickness. So what is bounded here? Bounded and fabrication pins and how it will be look like. Thermal conductive aluminum filled epoxy is used to bond planar fins on a grooved extension plate. Okay. So it is a greater fin height to gap aspect ratio is achieved with this method. Cooling capacity is increased. Cooling capacity is increased without increasing volume requirements. But epoxy has sorry. But epoxy has a much lower thermal conductivity, acting as an increased resistance. Folded pin. Aluminum or copper sheet metal is folded into fin. Okay, so this is the figure you can observe. And then attached to the base plate or directly to the heat surface. Okay, by abrasing or by using epoxy. Due to the availability of and fin efficiency, folded fins are not suitable for high profile heat sinks. Allows for the fabrication of high performance heat sink while extrusion or bonded fins are unacceptable. So these are the rectangular fins. Okay. So rectangular fins also have better performance than rounded fins. Pressure drop is also higher for rectangular fins. Rounded fins. So these are the rounded fins. Offer highest performance at higher values. So aluminum is the most common, followed by copper. So here it is having 4 to 6 X numbers, digits. It's more expensive. Suppose 3 digits means heavy, 2x means conductivity. So it is difficult to alter the surface of copper to improve radiations. External finish of aluminum is usually anodized or chromate of various colors. So see, this is the equivalent circuit or any circuit you can say. This is the thermal circuit TA, TS, TC, TJ. So all these are resistors are connected in series. You can name it as this is RSC. So between these two, RSC and RCS and RGC. This is the heat sink. You can see thermal circuit inside. So we'll see each notation one by one. Q equal to total power or rate of heat dissipation in W represent the rate of heat dissipation by electronic component during the operation. For this purpose, selection of heat sink, the maximum operating power dissipation is used. Tj represent maximum junction temperature of the device in degree C. Allowed Tj values range from 115 degrees Celsius in typical microelectronics applications to high 180 degrees Celsius for some electronic control devices. So TC case temperature of the device since the case of temperature device depends on the location measurements, usually represent the maximum local temperature in this case. Ts equal to sink temperature in degrees Celsius. Again, this represents the maximum temperature of heat sink at the location closest to the device. Ta is the ambient air temperature in degrees Celsius. So if you want to measure the thermal resistance, that is R equal to delta T by Q, where delta T is the temperature difference between the two locations. The unit of thermal is degrees Celsius by watt, indicating the temperature raised unit per unit by rate of heat dissipation. This thermal resistivity is analogous to the electrical resistance given by Ohm's law. Here with V represent voltage difference and I is the current. Thermal resistance between the junction and the case of the devices is defined as this is the junction and case. We already seen junction case temperature by Q. This is the difference between Tj minus Tc by Q. Suppose R is the resistance is specified by the device manufacturer. Although RJC value of a given device depends on how and where the cooling mechanism is employed over the package. So it is usually given a constant value. It is also accepted that RJC band the user ability to alter control. So K sink resistance C2S same as like that one. So this is the interface between heat sink and heat resistance also. So this is also improved substantially depending on the quality of making surface finish. So sink to ambient resistance, where is a heat sink thermal resistance value. If you want to calculate thermal temperature, you can use these formulas. So by adding all these uh, resistances, you will get total junction to ambient resistance is the sum of all three resistances. Finally, you will get Tj minus Ta by Q. So determine heat sink thermal resistances. We need to subtract from this change in temperature to the remaining resistance values. Here Ta is the cooling electronic equipment depending on the operating environmental conditions. Okay, all these things. And so see here natural convention and forced convention. So what is these two? Suppose if you are selecting a heat sink It is necessary to classify the airflow as natural or low flow mixed or high flow forced convections. So what is natural convection and forced convection here? Occurs when there is no external induced flow and heat transfer relies slowly on the free buoyant flow of air surrounding in the heat sink. Forced convection means occurs when the flow of air is induced by mechanical means, usually a fan or blower. So design considerations, the following cases are always increase the thermal performances. Longer and fin height, longer heat sink in the direction of airflow, increase number of fins. All these, all of these are false. Longer fin heights or longer heat sinks increase the surface area, but with fixed volumetric flow rate, performance may actually decrease with height. Okay, longer heat sinks means the direction of flow of air and more fins both means increase the surface area, but have adverse effect on pressure drops and flow bypass, and the average heat transfer quotient goes down. Okay. So finally, I want to tell you what I want to tell you means. Finally, so here heat dissipation is also a critical aspect. Heat dissipation is a critical aspect of electronic system design. So as circuit become denser and power levels rises, managing heat effectively is a crucial to ensure reliability performances and lifespan of electronic devices also. So what are the sources of heat in electronics? So joule heating due to current flow in conductors, switching losses in transistors and power devices, leakage current in semiconductor devices, resistive losses in interconnectors and PCB traces. What is third one is thermal failures. So thermal failures are reduced by using the heat sinks actually. So thermal failures. Suppose excessive heat leads to increased failure rates. So performance degradation in analog also digital circuits. Thermal runaway in a power electronics. Heat transfer mechanisms. I already told you like heat sinks and chips. Conduction through solid materials and conventional heat transfer surrounding fluid. Next one, radiation. Emission of energy to the environment. Minor in low temperature. Thermal resistance model. Used model as a heat flow path from junction ambient by using some resistance values. Heat dissipation techniques like heat sinks, thermal via spreads, active cooling like fans, blowers, advanced cooling, heat pipes, liquid cooling, thermoelectronic coolers, heat dissipations like materials, surface area, and fin geometry like that. So PCB thermal design strategy when you are considering adding copper core under hot components, increasing number of thermal wires using thicker copper layers. So I want to conclude this. Effective thermal management improves system reliability and performance. Early stage thermal analysis is crucial in modern high density designs. Okay. Uh, So finally, I want to conclude this course. Uh, we had completed our course with the help of those 10 lectures. So we have explored the fundamental principles, methodologies, and tools used in design reliable and efficient electronic systems. We had studied component selection, schematic and PCB design, thermal management, EMI, ESD protection, and system level integrations. And this course also provide the bridge gap between theoretical electronics and the real world design practices, so that we will see with the examples only, not on any software tool. So by understanding not just how circuits work, but how they behave under real world constraint, how measurements should be taken, what type of reliability analysis you have to do, all these we had discussed. So you are now uh, equipped to approach design challenges, any devices like embedded systems, IoT devices, communication hardware, and more. So this ESD not only particular to electronics, the circuits where you can use in different different that also you can do. So you always remember a good electronic system is not just about functionality. It must be robust, scalable, cost effective, and safe. So if you are whether into industry, suppose you are getting a job in the company or research area, let this course be foundation for deeper innovation, critical thinking, and responsible engineering. Thank you all, and I wish you success in your future endeavors in the field of electronics. Thank you.